We want to talk here in section 4.1 about exponentials. So we have talked a lot about linear functions, and we've also talked about power functions. Remember that a power function is y equals x raised to some power. So the variable x appears as the base of the exponent. Now in an exponential function, we switch where the variable x appears. So y equals 3 to the x power is an exponential function. And so these have very different characteristics, and we have to try to keep them straight in our own mind. So we said that linear functions, remember, so linear functions, and let me change that color too, because I'm not really talking about a power function here right now, but linear functions. And remember, a linear function is something that's going to look like f of x equals mx plus b. So it's going to be something that's a straight line. Linear functions have constant rates of change. Constant rates of change. And so, for example, if you have, if we do an example, suppose you have $100 and you spend $8 each day. $8 each day. So we would say then the amount of money you have, we could either say like y equals mx plus b. The b is what you started with, that's the 100, and you're losing money each day, you're spending money each day, so it would be y equals 100 minus 8t, or if you wanted to make it more like the amount of money you have is 100 minus 8t, or you could even write it with the function notation as a of t is 100 minus 8t. So what you call your variables and how you write that is more about how it looks, its appearance, rather than the meaning there. But you can see that's going to be linear. Now an exponential function, an exponential function has a constant, it increases or decreases by a constant percent. So exponential functions increase or decrease by a constant percent. So, for example, if you have that $100, so you have $100, and say you're going to, it's going to earn, you invest it somewhere, and it's going to earn 5% per year. And the investment earns 5% per year. So I'll walk you through just a little bit how it goes mathematically there. So you start with 100, and then after the first year, you're going to get 5% of that $100. So that means you're going to get 100 plus 0.0, I'm not 0.05, it's going to be 0.05 times 100 will be that 5. So you have $105 at the end of that first year. Now we could say that $105 came from, if you look back here and factor out the 100, that's 100 times 1 plus 0.05, or 100 times 1.05. So that's where we are after 1 year. Now the next year you're going to have $105 to start with, and then you're going to earn 5% of that $105. And so we're going to write that then, factoring it as 105 times, and then we have that 1 plus 0.05 again. But remember that 105 came from 100 times 1.05. That's the $105 there, times another 1.05 is going to make that 1.05 squared. And so what you see is that the amount we will have after t years is going to be, and we can write this in functional notation if we like, the amount is equal to that initial amount we started with times 1 to 1.05 raised to the however many years down the road that we have. And so that's our exponential equation. Now in general, any exponential, let me switch colors here. So any exponential, almost any exponential equation can be written as y equals ab to the x, or y equals ab to the t, whichever way you want to call it. But this b is really important because this b contains this 1 plus r, or it could be even 1 minus r in the case where this is decreasing. So the percent at which our amount, in our case we called it the amount of the value of the money, that is, this r is the percent in which it's increasing each time period. Usually we think years, but sometimes we may do something a little bit different. So the b holds that information, and the a is the starting amount, what you have at time 0. And so a is often called the initial amount. So it's going to be where you start, and then the b holds that information, that percent increase or decrease in that by whether it's bigger or smaller than 1. So another example here. So a car, if I can get my pen to work here, a car decreases in value by 20% per year. It's called depreciation. It decreases in value. So suppose a new car costs and is worth, we will say, $25,000. Then what we have is, after 1 year, our car, the value of our car, I'll say value, will be worth the $25,000 it was to start with, minus 20% of that $25,000. And so again, doing our factoring, we're factoring out that initial amount. There's that 25,000, and what will be left will be that 1 minus 0.2, which we can then write as 25,000 times 0.8. So when that number is less than 1, when our b is less than 1, then you can see that b is the 1 minus r. You can see the percent at which it is decreasing. And of course, then after 2 years, you can see how this is going to work. The value will be the value that it was, that 25,000 times 0.8, that's what it was after the end of the first year, and then we're going to lose 20% more of that 25,000 times 0.8. Kind of hard to write that. And so you can see that if we factor out that 25,000 times 0.8, what's going to be left is the 1 minus 0.2, and there's our next factor of 0.8. And so we have, after 2 years, it's going to be worth 25,000 times 0.8 squared. And then hopefully we can see after t years, it's going to be that initial amount. So there's in our a, b to the t, you can see that initial amount, 25,000, and then the b is going to be that 0.8, which you can see that b holds the 1 minus r to the t power. So we can tell that when we have y equals ab to the x, that's the b is going to be is sometimes called the growth factor. So our book likes to call this the growth factor. And it will hold when b is bigger than 1, then that b will be 1 plus r. And when b is less than 1, then the b is going to be 1 minus r. But either way, you can find out what percent it is increasing or decreasing by looking at b. And then, of course, the a is still that initial amount. So that is the amount at time 0, how much we have to start with. Okay, I'm going to go to a new panel here. And so let's look at some different examples and see if we can pick out the initial amount and the growth factor. So if we have, say, y is equal to 30,000 times 1.07 raised to the t power. So first question is it growth or decay? Can you tell? And then the next question is going to be by what percent does it increase or decrease? By what percent does our equation, does y increase or decrease? Can you tell what is the initial amount? So I'll just say initial amount question mark. Okay, so what we can see in the first one, hopefully, because the base is bigger than 1, it's going to be a growth function. And because if we subtract off the 1, we get 0.07, and if we make that to a percent, that is going to be a 7% increase. Whoops, didn't mean to erase that. So I was trying to underline it. So it's going to be a 7% increase. And the initial amount, we can tell from what the value is at time 0, and that's going to be the 30,000. Okay, let's try a different one. So if we say y is equal to, we'll say 50 times 0.89 raised to the t, that's supposed to be a 9. And can we answer those same 3 questions? Is it a growth or a decay? Is it, by what percent is it increasing or decreasing? And what is the initial amount? So again, in this one, we can see that because the base, so we're seeing this as y equals ab to the t power. So the base holds the percent increase or decrease. Since that is less than 1, it will be a decay. And if we take the 0.89, and if you subtract 1 from that, you'll get a negative 0.11. And so that is going to be 11% decrease each year. So that's the percent at which it is decreasing each year. And the initial amount is still going to be what we get when we plug in 0 for t. And so our initial amount is going to be 50. So let's look for a moment at, we're going to graph y equals 2 to the x and just look at some of the features that we can see from the graph there. Using our, in particular, we want to talk about increasing, decreasing, and is it concave up or concave down. So when x is 0, 2 to the 0 is 1, so it's going to contain the point 0, 1. When x is 1, it's going to be 2. When x is negative 1, 2 to the negative 1 is 1 over 2 to the first is 1/2. And then as we keep going, it's going to look something like this. So this is our kind of classic exponential growth. We see that we have a horizontal asymptote at the x-axis, which is the line y equals 0. We can see that this is going to contain the point 0, and it's going to rise from left to right. So we can tell that one of the key features about an exponential growth is that f is, remember symbolically we say arrow up means f is increasing, and we can say that for all x, so it is rising from left to right always. If we look at the rates of change, so if I look for right here, those 2 points, the rate of change, remember that's going to be our change in y over the change in x. Let me write that other point down. This point right here is negative 1/2. And so the rate of change, if we take 1 minus the 1/2 over the 0 minus negative 1, we're going to get a 1/2 over 1, which is 1/2. So that's the rate of change there. If we look at the next point there and look at that rate of change, then since that point has coordinates 1, 2, we can see that we'll go 2 minus 1 over the 1 minus 0, and so that's going to be 1 over 1, which is 1. So you can see that those rates of change are increasing. So the rates of changes are increasing, and I think you can see visually too. So that is how we can say then that our y equals 2 to the x is concave up. So that function is concave up. So here's an interesting question, kind of a challenging one here. Let's say if an investment increases by 4% per year, increases by 4% per year for 10 years. Trying to erase that comma, I didn't really need it. So for 10 years, what total percent did it increase by? Now, at first glance, it may seem like, well, if it increased by 4% each year for 10 years, it's going to be 4 times 10 is 40%. But what we're going to see is that's not actually the case, because we're going to see some compounding going on there, that the increase we get in the first year is going to get a chance to earn interest in the second, third, fourth, all the way through the 10th years. So what we're getting here is, if we can think of our equation, ab to the t power, then what we have talked about in here is that we don't know what the initial investment was, so I'm just going to leave it as a. But since it's increasing by 4%, then we can write that as 1 plus 0.04 to the t power. This is how we're going to find our base, because we know it's going to hold in that b, it's going to hold the percent increase or decrease. So this is going to look like y equals a times 1.04 to the t power. Even though we don't know what that initial amount is, it's going to turn out that doesn't really matter. So in 10 years, we're going to say, let's put t10 in there for the t, and so this will then become y equals a times 1.04 raised to the 10th power. Now we can put this into our calculator. Whoops, that's my left hand touching the screen where I don't want it to. So that when you do that, you are going to get something like, I mean, it's going to be messy, but it's going to round to, say, 1.48. So what we're saying then is whatever that initial amount was, which we don't know, after 10 years, it's being multiplied by this 1.48. So that means we are 0.48 above 1, right? That is, if we wanted to subtract, if we said the 1.48 minus 1, because if that had been a 1, that means we would just have exactly what we started with. But we are 0.48 times as much, that's how much is increased, which is a 48% increase. So the reason it's more than that 40%, again, is what we call that compounding, because you earned 4% on the first year, that got added to your principal, so that got it added into the A, and the next year it earned another 4%, and that got added in, and so on. Okay, very good.